All right, physics team, let's talk about the materials from days 4 and 5, the last chunk of your circular motion questions. So number 1 says, if you lose your grip on a rapidly spinning merry-go-round and fly off, in what direction will you fly? And I'm hoping we've talked about this enough times already that you know it's off on a tangent, right? Straight off. So if this circle represents your merry-go-round, let's say this is you at this, oops, hold on, this point right here. If your merry-go-round is going around this way, you would not go that way, of course, right? You would continue straight if you let go at that point, and you would fly off straight on a tangent because of your inertia, right? All right. A ladybug sits halfway, next one. A ladybug sits halfway between the axis and the edge of a rotating turntable. What happens to the ladybug's speed if? Part A says the RPMs has doubled. So what that means is that it's spinning around twice as fast now. If you spin it around twice as fast, that means you are cutting your time in half. Okay, so think about that. You cut the time in half. Cut the time in half. All right, when you cut the time in half, think of it like this. If you're traveling 30 miles per hour, your speed is 30 miles per hour. But now if you travel that 30 miles in a half hour, your speed is actually doubled. That means that you're traveling at 60 miles per hour. So if you cut the time in half, her speed actually would double. And on to the next one here, part B, if she sits on the edge, sitting on the edge, think about the circumference. The circumference of your circle is going to be bigger if the ladybug sits at the edge. So if you have a greater distance, now your speed is going to increase. It's like instead of traveling 30 miles, now you're traveling 60 miles. You increase your distance, so you're traveling faster. And if both A and B occur, it would be 4 times greater because it would be like doubling the effect. You have faster speed because your RPM is doubled, and you have faster speed because your distance is increased. So if you have faster speed, due to less time, and faster speed due to greater distance. So greater distance, less speed, less time. Yikes. One more time here. So if you have greater distance and less time, your speed is going to be 4 times greater for that one. All right, number 3 is a little bit weird. If the speedometer in your car is driven by a cable, and I know all you car people out there are probably saying that's not true. Sorry, I don't know. This is just the problem we have. If it's driven by a cable connected to a shaft that turns the wheels, will your speedometer be more or less than the actual speed when the car's wheels are replaced with smaller ones? So I picture it like this. If you have a smaller wheel, like think of one of those tiny little bikes that kids ride, those wheels have to turn around a whole lot of times in order to go the same distance as someone who rides on a bike with a bigger wheel. So if your circumference is smaller, your speedometer reading is going to be larger than it should be because your wheel is turning around so many more times in order to go the same distance than a big wheel would. For number 4, if you keep in mind this idea from the previous question, if a taxi driver wishes to increase his fares by adjusting the size of his tires, should he change to larger tires or smaller ones? So my thought on this was smaller tires, because smaller tires are going to turn more times. It's going to look like he's going a further distance, whereas he's not going as far because the smaller tires are turning around more times. So it'll look like he traveled a greater distance. And this is, of course, if your taxi driver is charging by the distance or by the mile. Okay. Number 5, washing machine, if we're talking about washing machines. Now, washing machines have small holes in the sides. Here's your picture. So there's a bunch of holes on the outside drum of a washing machine. As the washing machine spins around, if you've ever done laundry, and I hope you have done laundry, if not, you should do some. When you take your clothes out, the clothes are all smashed along the outside of the washing machine. And it's because as the washing machine spins, inertia, right? The objects want to move out. They want to continue to move in a straight line. So they actually look like they get forced out, but they're trying to move outward in a straight line motion. The inside of your washing machine has a whole bunch of holes, right? What fits through those holes? The water. Your clothes, thankfully, do not. So your clothes stay in the washing machine, the water goes outside. And then the water collects in the outside drum, and then it's drained out of the washing machine. So same kind of idea here for number 6, the spinning swings ride. Really great ride at Great America. We're not going to be going probably, but why do the swings go outward during the ride? It's all about inertia again, okay? When would the force have to be the greatest? When they are moving the fastest, because the highest speed would give you the greatest acceleration. Because you have this relationship, circular acceleration equals velocity squared over r. So when they're moving the fastest, you're going to have a greater acceleration. Greater acceleration is going to give you a greater force. Because we have this relationship, right? Newton's second law of force equals mass times acceleration. So greater acceleration, greater force. And here, greater acceleration caused by greater velocity. For the last chunk of this, I thought I would just go through the problems that I already worked out. It's much easier writing them on paper than writing them on my screen. So for number 7, a 615 kilogram car completes one lap in 14.3 seconds around a circular track with a radius of 50 meters. See, I underlined a couple of important points there. During this time, the car is moving with a constant speed. So what's the car's circular velocity? So you had in your equations, velocity equals circumference over period. That's a T right there. T for period, which is the time to go around the track. Or time to make one lap. So just plug in the info that you have. 2 times pi times r is going to be your circumference. So 2 times pi times 50, because 50 is your radius, divided by the time to go around one lap is 14.3. You end up with 22 meters per second. For part B, when you're looking at the acceleration of the car, use that relationship, acceleration equals v squared over r. So take your velocity you got up there and square it, divided by your radius, which is 50, and you get an acceleration of 9.68 meters per second squared. When you're looking at force, this is just Newton's second law. Force equals mass times acceleration. So take your mass of 615 kilograms times your acceleration, and you get 5,953.2 newtons. Okay, so that's number 7. For 8, an athlete whirls a 7 kilogram hammer tied to the end of a 1.3 meter chain in a horizontal circle. This is probably like a track and field type of event thing. So what's the centripetal acceleration of the hammer? So again, we're doing acceleration, centripetal acceleration, v squared over r. We don't know the velocity, but we know this relationship, velocity is 2 pi r over time. So you're just plugging in 1.3 is going to be your radius. So if you think of the hammer on the end of the chain as it makes one circle, right? It goes from the end of where you're holding on to where the hammer is at the end, and it circles around. And as it circles around, that's going to be your radius, the length of that chain. So that's how we know that right there. So your radius is 1.3. It says 1 revolution every second, so your period is 1 second. So when you calculate that out, you get 51.3 meters per second squared. So pretty big acceleration. And the tension in the chain is going to be mass times acceleration. So 7 kilograms is your mass times your acceleration. So you get 359.1 newtons. So pretty decent amount of tension. For number 9, the spinning carnival ride where you spin and the floor drops out has a radius of 2 meters and rotates once every 0.9 seconds. So what's the speed of a rider on this ride? So again, it's just applying this equation, 2 pi r over time. So 2 times pi times your radius, which is 2 meters, divided by 0.9, which is your period, okay, time of rotation, so you get 13.9 meters per second. Okay, so when we are trying to find the centripetal acceleration then, it's again application of that equation. So v squared over r, velocity is 13.9, so you square that over your radius of 2, and you get an acceleration, a centripetal acceleration of 97.48 meters per second squared. Now you're thinking that's an insane acceleration, but remember it's circular acceleration, it's mostly due to change in direction. For part C, when it says what produces this acceleration, if we're talking about for the person on the ride, it's actually the friction between the person and the wall. If you didn't have enough friction, you would not, spin around the wall. Think of it like if you wore one of those really shiny track suits or whatever, the swishy pants, you wouldn't have as much friction. You just would like slide down the wall. The wall could slide from underneath you. Okay, so for number 10, this is kind of an involved problem, but it's not so bad. So friction provides the force needed for a car to travel around a flat circular racetrack. Okay, you can't travel fast in a car if there's not enough friction. That's why tires are important. What's the maximum speed that a 600 kilogram car can safely travel if the radius is 80 meters and the coefficient of friction is 0.4? Okay, so you want to think about these forces here. You'd have gravity pulling the car down and the normal force pushing the car up. And friction is the other force. Friction is what causes the car to accelerate around the track. If there's not enough friction, the car won't accelerate around the track. So I listed out the stuff I know. I know my mass, my radius, and my coefficient of friction. I know that the force of friction, this equation is that mu times F normal is equal to my friction force. I know from my diagram here that the normal force is equal to the gravitational force. And so I can say the normal force equals mass times 9.8 because it's equal to gravity. And so it's 5,880 newtons. So from that, I'm able to calculate my force of friction, which is mu times F normal. So 0.4 times 5,880. So I get a force of friction of 2,352 newtons. Which, by the way, that's really small because the coefficient of friction of 0.4 for a car tire is ridiculously small. But you know. Anyway, so we get our centripetal force is equal to our net force, right? Because our force of friction is our center-seeking force, you can see up here, and that is equal to our centripetal force, which is the net force. So you say your net force is mass times acceleration. Mass we know was 600, and our acceleration, circular acceleration, we're saying v squared over r, so our velocity squared divided by the radius. And so then you can solve that out, and you end up with a maximum velocity of 17.7. So the fastest a car could go around that circular track, if your coefficient of friction is only 0.4, would be 17.7 meters per second. Hope that helps you guys out. Next week, we're on to some more labs. Again, always please email me if you have questions. I'm willing to video chat with you, go through things, no problem. Bye, guys. Have a great weekend.